Hello, my name is Gabi Slavcheva. I'm Quantopticon's Chief Scientific Officer. Today I'm going to show you how to install Quantillion, Quantopticon simulation software, and how to create your first project. Quantillion is distributed as an archive, a zipped file, which needs to be downloaded in your working directory, suppose that it's Quant, and unpack it in this directory. Upon unpacking the files in this directory, you will see all these files, and in order to start the program you need to run the run batch file, which launches the graphical interface. The next step is to create your project. This is done by pressing new config and providing the file name for the project, for example 4levels_Tryon, and pressing OK. Now we need to save this file in the working directory, which is Quant. So we select Quant and save it there, and you can check that the project has been created in the directory. And if you go inside this directory, there are three subdirectories: results, in which the results are written; discarded results, which serves to visualize the results on the fly, whereby a certain number of points is discarded in order to visualize it on the screen; and continue directory, where the results of the last computational time step are saved, and from this time step we can continue on in case that we want to continue the computations for longer times. Now we have to set up our quantum system. Our simulation software describes optical pulse interactions with discrete energy level systems, such as quantum semiconductor nanostructures, atomic systems, or defects in crystals. We have to set up the energy level structures of the system under consideration, which is done from this drop-down menu. Depending on the energy levels which are used to map any particular system, we can describe systems with levels from 2 to 16 currently. The maximum number of levels which we can describe is 16. So we use a real vector representation of the density matrix, so we can calculate the number of the population terms in this real vector representation directly, which depends directly on the number of levels considered. Let's consider a 4-level system. Then we will have 3 population terms. The next field is the resonant dipole density per cubic meter. This is the density of the resonant dipoles, which may be, for example, quantum dot surface density, which has to be converted into volume density. We can also describe just a single dot or a single resonant dipole within the simulation domain. Now we have to set up the 4 levels, which is done from this left-hand side panel, level configuration. There are 2 buttons, plus and minus, which add or subtract levels. With plus, we can add energy h omega 1, 2, 3, and 4. And with for a particular system under consideration, which might be, for example, biexciton cascade in a quantum dot, which is a non-degenerate 4-level system. The ground level is level 1, the y-exciton level is 2, the x-exciton level is 3, and the biexciton level is the 4th level. So for this particular structure, this particular energy level structure, we can define the energies again from the middle panel by pressing plus and taking the energy separation between the pair of levels, which are known either from experiment or from microscopic calculation. For example, h omega 2 minus h omega 1. Omega 1 is always the ground state. H omega 1 is always the energy of the ground state, and all energy levels are measured with respect to this ground state energy. So the value For this particular transition 2-1, this is the energy separation between the Y exciton and the ground state, and we know this value from either from measurement or from calculations. It's 1.365975 in electron volts. So we can the measurement unit can be electron volts, milli-electron volts, or microelectron volts. So in this case it's electron volts. Then we can describe the system by the second energy separation between levels 3 and 1, for example, 3 and 1. And the value here is, this is this energy separation between level 3 and level 1. The value is 1.366 electron volts. Again, we know this value from experiment or microscopic calculations. And finally, we know what is the energy difference between level 4, the biexcitonic state, and level 3, which is the exciton, as from this picture. 3 is the x-exciton and 4 is the biexcitonic state. This energy difference is 1.364 electron volts. Now we can visualize the system by pressing show level diagram. So you can see that these are 4 non-degenerate levels. However, not all transitions are allowed, dipole allowed, and in order to take into account this, we have another matrix which is allowed transition, which we need to fill with the optically dipole optical transition, optically allowed transitions. For example, transitions 1 to 2 and 2 to 1 are allowed. So we tick 1, 2, and automatically, because it's a symmetric matrix, 2, 1 is ticked as well. Then transitions 1, 3 and 3, 1 are allowed as well. So we tick 1, 3 and 3, 1 is also ticked. And transitions 3, 4 and 2, 4 are also allowed. So 3, 4, for example, is this one, and 2, 4 is this one. So we can show again the level diagram, which shows now the optically allowed transitions between levels 1, 2, 1, 3, 2, 4 and 3, 4 by these double-headed arrows. We can exit this drawing mode by pressing the back button. If we want to describe a degenerate level system, such as for example the trans state in a charged quantum dot, here this system represents two coupled two-level systems with the same energy of the excited states 2 and 4 and the same energy of the ground states 1 and 3. This particular system can be described in the following way. We still have 4 levels. However, in order to account for the degeneracy of level 1 and 3, we separate them by a comma. So here we put a comma. And 2 and 4 are again degenerate, so we separate them by comma 2. And then level 3 and level 4 are left blank. We still have 4-level system. Here we have to set up the energy separations between level 2 and 1, which for this particular system is 1.388 electron volts. The difference between level 3 and 1 is 0 because they're degenerate levels. So we set 0 here. And the difference between level 4 and 3 is the same as the difference between 2 and 1. So these are two degenerate systems. So we set 1.388 electron volts. Now we have to set the dipole allowed transitions, and in this particular system, dipole allowed transitions are between level 1 and 2 and between levels 3 and 4. So we need to tick only these elements in the matrix allow transitions, which corresponds to these transitions. And these are 1, 2, and 2, 1. 1, 3 is not allowed, so we untick it. And 4, 2 is not allowed either, so we untick it. And now we can visualize the level diagram, which shows 1 and 3 as the degenerate ground states of the system, and levels 2 and 4 are the degenerate excited states of the system, and the dipole allowed transition is between these pairs of levels 1, 3 and 2, 4. So we can now go back and set the longitudinal relaxation times. These are the relaxation times which correspond to dissipation in the system. The longitudinal relaxation times are the so-called T1 times, or the times with which the population of the excited level relaxes to the ground level. And the transverse dephasing rates are the polarization relaxation rates, or these are the rates with which a polarization decays between the pair of levels decays. So we can set the longitudinal times for this particular system in this matrix, longitudinal relaxation times in seconds. There is a scale factor which can be picoseconds, 10 to the minus 12, femtoseconds, nanoseconds, microseconds, and milliseconds. The relaxation times, the longitudinal relaxation times of the trans systems is on the order of picoseconds. So we set, for example, 2-1. This is the spontaneous emission time from level 2 to 1. It's measured 820 picoseconds. We have also 1-3. 1-3 is the spin relaxation rate. This is the spin flip rate between the electron in state 1, which is spin down, and the electron in state 3, which is in spin up state. So this relaxation rate is measured to be on the order of magnitude of 500 picoseconds. So we set up here 500 picoseconds. And also 1-3, because it's a symmetrical rate. Then we have the 4-2 and 2-4. 4-2 and 2-4. This is the relaxation rate with which the whole spin flips in the upper state due to phonon-assisted processes, and it's known to be on the order of 170 picoseconds. So we put here 170 as well as here. And finally, between level 3 and 4, we have a spontaneous emission rate from level 4 to level 3, which is again equal to the spontaneous emission rate of level 2 to level 1. So we can put here 850 picoseconds. Now we have to set up the transfer dephasing rates. That is the rates with which the polarization decays between any pair of levels. So, for example, for level 2 to 1, the net polarization decay rate is 340 picoseconds. The same is valid for 1-2 and 2-1. For level 1-3 and 3-1, the corresponding level, polarization decay is 450 picoseconds. For level 1-4 and 4-1, the polarization decay rate is 340 picoseconds. And it's the same for level 3, 2 and 2, 3. It's a symmetric matrix. And for all other rates, we assume that it's the same. Of course, these values are either measured values or calculated values from microscopic calculations. Once we have set up this transfer dephasing time matrix, which is again in picoseconds, but we can change the scale from this drop-down menu, we have to set the dipole moments of the allowed transitions, and these transitions are between levels 1 and 2 and 3 and 4. So the dipole moment can be calculated microscopically or can be inferred from experiment, and it's 9.15319 10 to the minus 29 coulomb meters. The dipole moment is measured in coulomb meters in SI, and it's a symmetric matrix. Between levels 3 and 4, we have the same dipole moment, 9.15319 10 to the minus 29, and this is again the same value. Now we have set up all parameters of the quantum system, including the dissipation in the quantum system and the interaction with the environment. The next menu is used to set the structure geometry. Regarding the longitudinal relaxation times table, I should note that all coherently driven transitions such as 1, 2, which are possible upon pulse excitation but are not decay rates, should be set to a very large number, ideally infinity. So, for example, the transition between level 1 and 2 and 3 and 4 should be set to infinity practically. So 1 times 10 to the 100. Between 3 and 4, also 1 times 10 to the 100. And all other transitions that are forbidden, such as 2, 3 and 1, 4, should also be set to infinity, or 1 times 10 to the 100. 1, 4. 2, 3. 3, 2. And 4, 1. All these cross transitions are forbidden. Once we have set up all parameters of our quantum nanostructure, in this particular case, we are considering the trance state in a charged quantum dot, we can embed the quantum dot in a particular photonics geometry. Let us consider a micropillar geometry. So we have a charged quantum dot embedded in a lambda cavity in this micropillar geometry. In order to construct the geometry, we have to use the menu structure geometry. And here we have to provide the discretization, the spatial discretization of the structure. In this case, because we are dealing with quantum dots, the size of a quantum dot is very small, about 4 nanometers high. So we need to provide a very fine discretization. Discretization in this case is 1 times 10 to the minus 10 in meters, or 1 angstrom. The wavelength, the central wavelength of the driving pulse is 894 nanometers, and we have to provide also the shrinking percentage of the aluminum oxide layers, if there are such layers in the structure, since such layers experience shrinkage during the processing. So we have to account for this shrinking during the fabrication process and during the fabrication of the whole mirror structure. Now we have to construct our photonic structure layer by layer using the built-in constructor. We start with the first layer in our structure. We will assume that the structure is gallium arsenide, aluminium gallium arsenide DBr structure. So we have to select first whether we are constructing the bottom DBr stack, the cavity, or the top DBr stack. Let's start with the bottom DBr stack. And we have to consider whether there are sublayers or not in this structure. The first layer is a substrate, so there is no sublayer. And we can define the structure, the layer thickness, which can be, for example, 1.3 microns. In nanometers, this is 1,300 nanometers. Then we can add a comment, for example, gallium arsenide substrate. And in order to calculate the refractive index, we can either set it up manually from this field here, or calculate it using the built-in program, depending on the wavelength and on the composition of aluminium. And for example, for gallium arsenide layer, the aluminium composition is 0, so we can set up 0 here, and tick this field so that the program calculates the refractive index. So we have the first layer and we have to add it. So we push add layer, and we can also show the graphics by pressing show graphics button. So this is the first layer, which is a very thick layer. Now we have to construct our bottom DBr stack, starting with aluminium arsenide layer and a gallium arsenide layer that are alternating within the bottom DBr stack. So we start with the first layer, aluminium arsenide. If we do not input any value for thickness, the program assumes that we are constructing a quarter lambda layer. So they will take lambda, the wavelength, and divide by 4 times the refractive index. And the refractive index is calculated automatically from the built-in program here, if we tick this field. So in this case, for aluminium arsenide, the aluminium concentration is 1. So we input 1 and we add this layer. This is our second layer. However, this layer has a sublayer of gallium arsenide, which will be repeated a certain number of times within the bottom DBr stack. So we have to input a sublayer, which is a gallium arsenide layer. We can also give a comment for this particular layer, and this is for example aluminium arsenide bottom DBr. Now when we want to add a sublayer, we can add this from this menu. So we have sublayers from 1 to 2 depending on how many sublayers we have. And we can either input manually the thickness of this sublayer or leave it blank so that the program calculates it as a quarter lambda sublayer. So in this case, this is the gallium arsenide layer. So we have to set aluminium concentration to 0. And we can also put a comment for this as gallium arsenide bottom DBr layer. And then we can add this as a sublayer. So now we have added this as a sublayer. And if we show the graphics, then we can see both layers, aluminium arsenide and gallium arsenide. So now we have to repeat it, say 25 times. In order to do that, we can select the number of times the sublayers are repeated from this drop-down menu. And for example, we want to repeat it 25 times. So we select 25 and repeat, and then we can update the layer in order to show it on the graph. In the graph, you can see this layer is repeated 25 times. Since the cavity is made of gallium arsenide, we have to add another half a layer, and this is the aluminium arsenide layer. So we put aluminium arsenide, bottom DBr, and we have set up already aluminium concentration 1. So we just add this layer here and show the graphics. You can see that now we have another half a layer of aluminium arsenide added. Now we have to construct the cavity. In order to construct the cavity, we have to select the type of the layer as a cavity. And depending on whether we want to construct a lambda cavity or a different cavity length, we can either input the cavity length manually or calculate it in order to be a lambda cavity. In this case, the cavity is a gallium arsenide one, so we have to input the cavity length of the half cavity in which the quantum dot is embedded, and it's 122 nanometers. For a comment, we can put gallium arsenide cavity. Then, since this is a gallium arsenide cavity, we have to set the aluminum concentration to 0 to calculate automatically the refractive index of gallium arsenide. And then we add the layer, and when pressing show graphics, we can see the half of the cavity layer plotted here. Now we have to input the quantum dot layer, which is a 4 nanometers thick layer. So we put 4 nanometers here, and as a comment, indium arsenide quantum dot layer. And here, because we cannot calculate automatically the refractive index of the quantum dot, we can input it manually. So we just untick calculate refractive index for all gas and input the value for the indium arsenide quantum dot refractive index, which is 3.696. Now, the quantum dot is an active layer. In order to account for this, we need to input the initial and equilibrium populations of our multi-level system. In this case, we have a 4-level system, so we have to input 3 population terms. And let us assume that all population is initially in level 1. So all levels are working in absorption. So, for example, the initial population upon excitation from level 1 to level 2 is the difference between the populations level 2 and level 1, which is 0 minus 1. If we assume that population is all in level 1 and the population is 1, then we should assume that the population is minus 1, initial population. The equilibrium population is usually equal to the initial population, unless we want to explore other dynamics, different dynamics. And here, these are the initial populations for all population terms in our real vector description. So in this way, we define the active layer in our structure. So now we already have the comment in indium arsenide quantum dot layer, and we have set up all population terms. So now we can add this layer and show the graphics. And if you scroll, you can see the quantum dot layer. The red dots are actually the left end of the quantum dot layer and the right end of the quantum dot layer, which are monitor points. So we want to monitor dynamics at these edges of the quantum dot layer. Next, we want to finish our cavity layer. So we just set the structure as a passive structure, that is, there is no population in this layer, in the cavity layer, beyond the quantum dot layer. And we can give the thickness of this layer, which is again 122. It's a symmetric cavity in nanometers. Then we can add the comment gallium arsenide cavity, and we can calculate the refractive index of a gallium arsenide with aluminium concentration 0. So we can add this layer and show the graphics. Here you see that the cavity layer is finished. Now we have to set the top DBR stack, starting with a aluminium arsenide layer. The aluminium arsenide layer is a quarter lambda layer, so we don't need to input thickness for that. The comment would be aluminium arsenide top DBR, and then we can calculate the refractive index inputting aluminium concentration of 1. So we can add this layer and show the graphics. We can see that this layer is already added, and this layer has another sublayer, so we have a second sublayer. This sublayer is a gallium arsenide layer. We don't need to give the thickness for that either. The comment would be gallium arsenide top DBR, and we can calculate the refractive index by setting the aluminium concentration to 0. So we add this as a sublayer. Now that it's a sublayer, not a layer. So we add this sublayer, and if we show the graphics, you can now see the two layers. These two layers need to be repeated 25 times. So we get, press repeat button, and then update layer or sublayer. And when we show the graphics, you can see that the top DBR layer has been created. Now we want to finish with an optical fiber. The optical fiber has a different refractive index, which we cannot actually calculate with a built-in program, and therefore we have to input this refractive index. The thickness of the optical fiber, let's assume that the thickness of the optical fiber is the same as for the substrate, the gallium arsenide substrate, so it's 1300 nanometers. For the comment, we can put optical fiber, and now we can input the refractive index, which is 1.436 for this layer. So we can add this layer and show the graph. So this is the last layer, layer number 6, which is the optical fiber layer. So now we have the whole structure constructed, the cavity structure with the quantum dots in the middle of the cavity. And this is a lambda cavity. The cavity length is equal to lambda over 4 times the refractive index of gallium arsenide. And now we can also insert different monitor points. You see that the spatial positions of the left and the right end of the quantum dot layer are shown here in unit cells, and there are also fixed spatial positions of at the beginning of the structure here, or at the end of the structure, which are fixed monitor points within the code. So we always sample the time dynamics at these spatial points by default. Now we can define further points by pressing Ctrl and left mouse button. We can define other monitor points. Here you see the red dot corresponds to this coordinate. We can if we want to monitor the dynamics in some other point within the cavity, we can add, or within the DBR stack, or wherever we want to monitor the time dynamics, we can add these points up to 10 points can be added here on top of the 2 final points of the simulation domain, which are always sampled. The monitor points are the spatial points at which the time dynamics is sampled, and we can delete them by holding Control and dragging a rubber band around the point and right-clicking the mouse. So we can add them by just holding Control button and clicking left-hand mouse button, or delete them by Control, drag and right-click. So in this way we have constructed the structure, which contains rectangular layers. In case that we want to implement graded interface, graded refractive index structures, we can tick this box, and in this case we have to provide the left and the right end point aluminium content in order to calculate the refractive index. So instead of having rectangular layers, we'll have a triangular layers or sawtooth shaped layers, and in this way we can implement such structures as well. In case that we want to implement oxidized layers, then if we apply a percentage in this field, for example 5%, this percentage will be, and if we tick oxidized box here next to the thickness of the layer, of the respective layer, this shrinking percentage will be applied to the respective layer. This program is quite flexible, fairly flexible. We can insert layers by pressing insert button, or insert sublayers, remove layers or sublayers, or even repeat the whole structure multiple times by pressing this button, repeat all. Now we have to move next to the input pulse sequence, where the pulse is defined, or the pulse sequence, the pulse train parameters are defined. The next step is to select the driving pulse parameters or the pulse sequence parameters, and this can be done from the input pulse sequence menu. We can launch a pulse sequence which consists of 1 to 10 pulses. Currently, for example, we can choose 3 pulses in a sequence, and for each and every pulse we can define the pulse parameters. For example, for pulse 1 in this sequence, we can define the pulse shape, which can be selected from this menu. And currently these are the choices: a continuous wave pulse. If we press apply, we can visualize the pulse on the left hand side panel. This is the pulse, or the CW wave in this case. In the middle panel, we visualize the Fourier transform of this pulse as a function of frequency, and on the right hand panel, this is the pulse as a function of the wavelength lambda, central wavelength lambda. So we can also choose a Sesh pulse or hyperbolic sequence pulse shape, a Gaussian pulse shape, or gain validation pulse, which means that the pulse is switched from 0 to 1 within certain number of periods, certain number of lambda. For example, within 5 periods, the pulse is switched from 0 to 1. And finally, Gaussian white noise pulse. So for this particular case of 3 pulses in a sequence, we can independently set up for each pulse the pulse shape. For example, for the first pulse, it's a Sesh pulse with a central wavelength 0.92 and left circular polarization, with pulse duration 50 femtoseconds, which can be either femtosecond or picosecond range. We can use the pulse area, which can vary from pi over 4 to 20 times pi. in order to calculate the initial pulse amplitude, or alternatively we can untick this box and set the initial pulse amplitude manually in volt per meters, and we can set the delay of this pulse in femtoseconds, picoseconds or nanoseconds. For example, in this particular case we have set up 500 femtoseconds for the first pulse. And when we press apply, we can visualize the such pulse, and this is a circularly polarized, left circularly polarized pulse. Now for the second pulse we can select a different pulse shape, let's say a continuous wave, and for the third pulse and the same characteristics. Pulse central wavelength, for example 9.5. Pulse, it can be linearly polarized, say Y linearly polarized. Pulse duration in this case, it doesn't have a meaning, and the delay may be a different delay in, say, picoseconds. So we can apply this second pulse. For the third pulse, we can choose, for example, a Gaussian pulse shape with some central wavelength 894, for example, with left circular polarization, pulse duration 100 femtoseconds, pulse area pi, and a delay of let's say 800 femtoseconds. And for each pulse we can also define the origin of the pulse, that is the spatial location from which the pulse is launched, and this can be done by pressing Ctrl and left mouse button, and this, as you see in this field position, the coordinate of this point appears, and if we press apply, then we know that this Gaussian left circularly polarized pulse will be launched from this position, and it will propagate in both directions. So we can set up different origin for each pulse in the sequence. Once the input pulse parameters have been set up in the previous menu, we have to impose the boundary conditions on the left boundary of the simulation domain and on the right boundary. Currently there are 4 types of boundary conditions implemented: absorbing boundary conditions, perfectly reflecting boundary conditions, and perfectly matched layers, as well as periodic boundary conditions. The same boundary conditions can be imposed on the right boundary as well. We can independently set the reflection coefficient of the left boundary manually and on the right boundary, and there are some grid settings which can be input from this menu. For example, the Courant stability parameter, which is a measure of convergence of the algorithm, can be changed here. We can also change the number of points per file which are saved every time that we print the results on the disk. For example, currently there are 10 million points per file which are saved. Every 10 million time steps the program will save the results, but we can change that. For example, we can input 2 million time steps here. This is the next field, is the number of monitors, the maximum number of spatial points at which the time dynamics are sampled, and currently it's 4, but we can change it, of course, depending on how many points we want to monitor at a time. The simulation usually starts from time 0, and we can change this value, and it's automatically changed when we continue the program from the last calculated time step, and I will show that in the results menu how to do that. We can also change the simulation end time in time steps. Currently it's 10 billion time steps, but we can also change this one. The maximum number of iterations within the predictor corrector method implemented is set from here, and also the accuracy of the numerical procedure can be changed from here. Once all structure geometry and input pulse sequence parameters as well as quantum system parameters have been set up, we can start running the simulations, and this can be done by pressing Start Calculations button. The program starts to be executed and it prints the current time step. The current time step is 2 million, so every 2 million points in time will be saved on the disk. In order to stop the simulations, we can press the button Stop Calcs, which will stop the simulations. We can visualize the data during the calculations on the fly. For example, we have performed some calculations and I can visualize them by selecting the time step, updating first, and selecting the time step that we want to visualize. For example, we want to visualize the first time step at 2 million time steps. On the right hand side, on the top right hand side corner, the field evolution at the input facet is shown, or at the output, depending on whether the pulse is injected from the left boundary or from the right boundary. For the current simulations, the pulse is injected from the right boundary. So this is the initial pulse. This is a Gaussian circularly polarized pulse, left circularly polarized pulse. On the left hand side top corner panel, we can see the output emission from the structure. And this is the emission at the output facet of the micropillar structure. We can also check the dynamics at the left end of the quantum dot layer and at the right end of the quantum dot layer, which shows initially the population is ρ11 is 1, so all population is in the ground state, and it starts to decrease while at the same time the population of level 2 is increasing. And if we sample the dynamics outside the quantum dot layer, there is no population change in this plot. This is just the field which is within the cavity. It's a passive calculation. The same is applies for the other point within the cavity that we have set previously a monitor to sample the time dynamics. Now, if we want to check a later time step, for example, at 6 million time steps, we just press Update, and the files are being loaded here. And we can see again on the top right corner the initial pulse at a later time moment. This time step corresponds to the second picosecond after the pulse, after the launch of the pulse. So here on the right hand side is the initial pulse, on the left hand side is the emission at this particular time moment, and we can see the population within the quantum dot, which performs Rabi flops. At the same time, we can see the spatial dynamics on the bottom left panel. So the pulse is injected from the right hand side, and it's a circularly polarized pulse. Therefore, there are two components, Ex and Ty of the pulse. And we can see the refractive index profile of the structure, very roughly displayed here. We can zoom in and slide in order to see the spatial variation of the fields and populations along the structure, as well as the refractive index profile. And we can locate the quantum dot position, which is here. So here within the quantum dot, the population is changing, as you see, and this is exactly the spatial dynamics, which is shown on the top, in the middle panels for the left and right hand side of the quantum dot layers. Now we can also sample the dynamics at the later time moment, let's say at this time step, which corresponds to the 224 picoseconds. We can update again and see the long time dynamics of the structure at the location of the quantum dot within the cavity, and also at two different locations, at the beginning of the structure, at the end of the structure on the left panel, and in the middle we can also choose between two monitors, which we have previously set in structure geometry, within the cavity of the structure. So the file is being loaded at the moment. This is the progress of loading the file, and at the same time the code can run without actually interrupting the code. We can visualize on the fly the calculations of the previous time step, or every previous time step which we have already calculated. And we can see now the time dynamics on top and on the top and in the middle panels, and spatial dynamics on the bottom panel. It takes some time because it's a very long simulation in time. So here is the pulse, the initial pulse, which is already reduced to just a line because it's a very long time scale. And on the left hand side panel, this is the emission of the cavity, the output facet of the micropillar structure. In the middle we can see the dynamics of the populations of levels 1, 2, 3 and 4. The population performs Rabi floppings between levels 1 and 4, and the population of levels 3 and 4 continues to grow, and it's not sufficient to show the growth of this. The time scale is not sufficient yet to show the growth of the populations of level 3 and level 4. If we want to stop the calculations, we can just press stop, and if we want to continue the calculations from a point in time that we have, for some reason we have stopped the code. Suppose that we have stopped the code at a certain point and we want to continue from this time moment on, then we can press continue calcs, and this button actually allows to copy the last time step files into continue directory, and the simulation starts to run from that point on. I should note that upon pressing the Start Calculations button, a file is created in the working directory called exec data, which contains all information preset in the graphical interface, including the structure geometry, describing all layers with the corresponding comments. The time dynamics can be used to calculate the transmission spectrum from the Fourier transform of the initial and final emission time trace, and also from the time trace of the populations inside the quantum dot layer. One can calculate the time and polarization resolved photoluminescence, and from the emission at the output facet, the statistical properties of radiation can be calculated, such as the correlations functions G2 and G1. Thank you for your attention.